Hey everybody, it's Ripley again. We're going to take what appears to be a step backwards on this, and we're going to go back and do some approximation of integrals. And the reason we want to do this is we want to introduce some new ideas, some new concepts. I want to plant some seeds here. So let's talk about how when we first learned about integrals, remember what we did? We took a function and we did something crazy with it, and this was f of x, and we wanted to figure out, we wanted to approximate the area underneath the function from a to b. You remember how we, whoops, a to b as opposed to a to a, sorry about that, you guys. And remember how we did it at first? We took a left rectangular approximation. Remember how that worked? And we looked at it, we're like, wait, I don't like the way that looks. This is going to be an under approximation, right? Remember that guy? And we called this L sub n. And this guy was approximately equal to the definite integral from a to b of f of x dx, but it was exactly equal to L sub n. Remember how this worked? You took delta x, right? And you took that times, and you did f of x naught plus f of x1 plus f of x2, remember this, plus dot dot dot, plus f of x sub, whoops, excuse me, f of x, excuse me, sub n minus 1, f of x sub n minus 1. Remember how that worked? Where you started on the left-hand side, you grabbed this guy, found the height, found the area of the rectangle. These widths were all the same, which was delta x, right? This was this one, and then we grabbed this one, grabbed the height, this one, grabbed the height, this one, et cetera, et cetera. Those were all called rectangular approximation methods, or creating Riemann sums. That was back in the day. Also remember that delta x is always equal to b minus a over n, right? If we want all of our subintervals to be the same width. Now you may remember again, excuse me, that when I look at this one, I'm like, wait, that's clearly under an under approximation. So what we did was we took a right rectangular approximation. Remember how this guy worked? And we just filled these guys in and clearly got an over approximation. Remember, r sub n equaled delta x, and then instead of starting at f of x sub 0, or I guess f of a, we did f of x sub 1 plus all the way up to f of x sub n. Now that time we started over here and built, whoops, and built our first rectangle. And then we grabbed this guy. Again, I know I'm repeating myself, but that's okay. Well, can you see how there might be a nice little in between? Remember how m sub n, remember how we came up with that? That was delta x. And then the way that your textbook says this, and I think I mentioned it in the last lecture, what they do is they just say f of x sub 1, the mean of that. So they take the midpoint, right? Remember how that worked? Plus f of x sub 2, the mean of it, plus, which is just the middle of it, plus f of x sub n, that guy right there. Easy peasy. However, people started saying, well, wait a sec. There's got to be a way to get more accurate. Now you may say, you may be having a conversation in your head, wait, why do we need a better way? Remember how rectangular approximations led to Riemann sums, led to infinite Riemann sums, which led us to integrals. Yeah, but you know mathematicians, we don't typically leave things alone. So let me show you a new idea. Let me show you a different idea that maybe you can play with. What if I took a function, so let's take this same sort of looking function, right? And this is f of x, and we're going to go from a out here to b, right? And we're going to cut this thing up into some intervals. Just keep these same looking, right? So all these are going to be the same width. This is going to be delta x, etc. These are all delta x. Okay? All right. Now, what's kind of begging to happen here? What's begging? Well, let's look real quick. If I could take, I'm going to grab an obnoxious color. Can you see where I can almost, like, I've got a trapezoid there. You see that? It almost looks trapezoidal. So what people started saying was, okay, if we can do this with simple rectangles, why can't we get a little more complicated with the type of polygons that we're going to use? Rectangle is just a polygon, right? So they said, wait, let's just build a rectangle. Well, how are we going to do this? Well, let's think about this. I'm going to label some points first. So clearly what we're going to do here is we're going to do a trapezoidal approximation with 4 trapezoids. So this is going to be T sub 4 when we're done. But we got to do some thinking here. I'm going to call this x sub 0, this point right here. I'm going to call this point x sub 1, call this point x sub 2, call this point x sub 3, and I'm going to call this point x sub 4. Notice that there's one there's, if you think about it, there's one more x value than there are numbers of subintervals, which makes sense because I've got them on both sides, right? All right, now, who remembers what the area of a trapezoid is? So area of a trap. Well, if I take this trapezoid right here, let's lay that thing out. Let's see what it looks like first. It's going to look kind of like that, isn't it? This is supposed to be a right angle. Sorry about that. Let's erase that so it looks a little more like it should. All right. Well, let's try and remember what the area of a trapezoid is. Area of a trap. You remember? Area of a trapezoid equaled 1/2 times the height times the sum of bases. So base 1 plus base 2. Remember that? That was, you proved that in geometry. If you didn't have geometry, hopefully you've seen it before. So it's really the average of the bases times the height. That's another way of doing it. And in geometry you did, well, we won't get into it. It's not geometry. But let's look at this trapezoid right here, and that's this guy here. What's the height? Well, we know that the x-axis is perpendicular to any vertical line. So the height on this thing is, let me erase and give myself just a touch more space, if you'll excuse me. The x-axis is perpendicular to vertical lines. So this guy right here, my height is actually delta x, right? It's this right here. My base 1, that's this guy right here. This is base 1. If you remember from geometry, we'll look at it. It's this guy right here, isn't it? Which is what? It's just f of x1, right? And this is my base 2. This is base 2. And what's that? Well, it's this guy, which is just f of x0, right? So the area of the first trapezoid, let's just call this a sub 1, is going to be equal to delta x, right, over 2, because it's half the height is delta x divided by 2, times the sum of the bases. So I've got f of x, what is going on here? Sorry, you guys. I just had lunch. I'm in a food coma. F of x sub 0 plus f of x sub 1. Now, let's look at the second one. Well, again, if I'm looking at this guy, now look at my height is still delta x. It hasn't changed. My base 1 this time is going to be f of x sub 2, right? And my base 2 is going to be f of x sub 1 again. So the area of the second one is going to be delta x over 2, that's the height over 2, times f of x sub 1 plus f of x sub 2. Starting to see the pattern? Look at that. A sub 3, we're going to write them all up. You're going to hate me for it, but that's all right. It won't take very long. Don't be haters. Is going to be same analysis. We're going to get f of x sub 2 plus f of x sub 3. Right? And then last but not least, a sub 4, the area of the fourth. This is a sub 1. This is a sub 2. This is a sub 3. This is a sub 4. So the area of the fourth trapezoid is delta x over 2 times f of x sub 3 plus f of x sub 4. Now what do you notice? I notice that f of x sub 0 and f of x sub 4 only got counted once. Everything else got counted twice, didn't it? So if I wanted to do, excuse me, good gracious, don't say Gesundheit, I can't hear you. If I wanted to do t sub 4, wouldn't this be a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, right? Which is just equal to, now I'm going to get a little crazy here with my algebra. Notice that they all have a delta x over 2. So I'm going to factor that out. Delta x halves, and then what happens? It's f of x sub 0 plus 2 f of x sub 1, it got counted twice, plus 2 f of x sub 2 plus 2 f of x sub 3 plus f of x sub 4. So if in general I wanted t sub n, I'm going to need a little space, but that's all right. T sub n, what would it be for any function? Well, it's exactly the same thing. Look, I'm going through the exact same process. I would get delta x divided by 2 times f of x sub 0 plus 2 f of x sub 1 plus 2 f of x sub 2 plus dot 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 plus 2 f of, now this is where it gets a little ugly notation-wise, f of x sub n minus 1 and then plus f of x sub n. See how that works? Notice the first one that I start on, x sub 0, and the very last one, notice f of x sub n, this n and this n match up. Everything else gets counted twice because notice that for A2, f of x sub 2 is the base, is base 1 for A2, but it's base 2 for A3, so it gets counted twice. Now that's pretty cool, huh? Okay, now let me kick over. This is called, by the way, as you could probably guess, a trapezoidal approximation. We're going to do a bunch of these. Approximation. And you may ask yourself, well, Ripley, is it really better, let's say, than the midpoint approximation? Is the trapezoidal really better than the midpoint? Well, that's pretty obvious that it isn't in this case, right? At least the midpoint, remember how the midpoint worked? It gave us a little too much and a little too little, right? So let me do one quick midpoint in red. Remember how that worked? You'd grab this guy, you'd go up to the top, and you'd build a rectangle. And remember, here I grabbed a little too much there, but a little too little there, and it ended up being pretty close. In this case, because of the behavior of the function, I am under-approximating every single time. So this guy appears to be an under-approximation, kind of like, in this case, a left-point approximation, or a left-sided approximation would be. All right? Now, I'm about to blow your mind, so be prepared.